Welcome to Lesson 4 of Week 1 of Julia Programming for Nervous Beginners. So this is the only theory lesson in the whole course, and that actually means it's very, very important. You really have to try and understand why computers work they do and what the relation is between programming and formal logic. So what I'm trying to explain in this lesson is that programming is actually an application of formal logic. And I therefore have to explain what I mean by logic and what I mean by formal logic and what the difference is between two, and try and give you an indication of how formal logic makes computer language and computer programming possible. So after this lesson, you should be able to explain what on this course we mean by the word logic and the difference between logic and formal logic. And you should be able to explain why any computer must embody formal logic. This lesson gives you a very small example of a language that applies formal logic to an extremely limited extent. And finally, you should be able to explain that computer programming is actually expressive in the same way as poetry and music. Okay, so why then this lecture? So beginners often find programming a really strange thing to do, in the sense that it's difficult for them to make sense of typing things in this way and why the rules are so strict and what you actually do when you are writing code according to these rules. I can't make that experience any less weird. The weird is actually part of this territory. But what I want to explain is that the weirdness is not arbitrary. It's not aimed at keeping people out. It is instead an essential aspect of any computer language. And so I hope that I can encourage you to persist with Julia and the Julia way of writing programs until they start to feel natural and the weirdness disappears. And when that has happened, you will have learnt a new language. And I'm totally serious. As I hope you will see below, Julia is as rich and expressive in its own right as any natural language, such as Spanish, Mandarin, Kung, your other languages, thousands of languages on earth that human beings speak. So there's no real difference between a computer language and a natural language, except that a computer language strictly observes formal logic. You could write advertisement, love letters, whatever in Julia, but because formal logic can be implemented on a machine, you can use it to write programs that make machines do things that you want them to do. That's really what the possibility that formal logic creates. Okay, so I'm going to define logic as the study of correct forms of reasoning. Reasoning itself, of course, is part of everyday life and language. It's simply the process of trying to make sense. And what, of course, is also the case is that there are very many ways to make sense, and many of them are actually mistakes in reasoning. What do I mean by that? For instance, if somebody says, "Oh, the grass is wet, it must be raining." That's a very natural thing to infer, but from the point of logic and correct reasoning, that's a mistake, because it is not always the case that the grass is wet because it has been raining. There are other things that can wet the grass. So it's not a strict logical conclusion that you can draw just because the grass is wet that it has been raining. And once one starts becoming aware that certain kinds of reasoning can lead to mistaken conclusions, the impulse is to start wondering, well, can we make a study of that? This is actually in at least 3 different traditions. This was done in very different ways, approximately 100 generations ago, in ancient China, ancient Greece, and ancient India. And to some extent, these traditions are handed down to us even today. Of course, in 100 generations, things really get added and subtracted and used. So it's not exactly, by any means, the same as it was then. But that's what I mean by the word logic, and that's different from the very many ways in which it's used in ordinary language. It's only, for me, the study of correct forms of reasoning. Okay, so once we've got the term logic, we can talk about formal logic, and that's then very easy. It uses symbols and formulae to do the study of reasoning. And that started maybe only 6 generations ago. The aim was to make absolutely precise how reasoning works and to be absolutely certain that the reasoning was correct. And the method used to make absolute precision and certainty possible were the rules of algebra. So formal logic is not exactly the same as algebra. The expressions can look somewhat similar, and the calculations proceed to some extent a little bit similarly at times, but there are completely different ways of doing those calculations. What it does, as a result, is that you don't actually need intuition or insight to understand logical analysis. You make it completely formal. And one of the results is that things that are completely obvious and things that are completely baffling can sit side by side. The examples of the obvious we'll give later in this lesson, the not, and or truth tables. The completely baffling takes a little while to explain, so we're not going to do it in this lesson or in this course. There's a book called Logic Comics. If you look at pages 164 to 168, you'll see a number of items about paradoxes, and there are quite a large number of paradoxes that have been expressed in formal logic, and they can be completely baffling. So the example that I want to make of formal logic is the not, the and or operators. So we're going to use two-valued logic. That's by far the most common. And that means we're going to work with only true constants, namely true and false. So these are constants, and if we want to interpret them in real terms, we have to have some kind of meaning for true and false in the real world or on a computer. But we'll just take for granted that we know what they mean. So a statement is then something that has either the value, have either the value true or the value false. So a statement is either true or false. So we need a formal symbol to stand for a statement. So we can use the symbol P to stand for the statement, the Earth spins on its axis, and the symbol Q to stand for the statement, the Earth is round. I've chosen those two because P seems to me very well established and indubitably true in the real world, and Q is merely an approximation. There are many ways in which the world is not round. If we want to say that Q is true, that is, that the Earth is round, we have to understand that we're kind of idealizing. We're talking about an Earth which we ignore mountains, we ignore the slight flattening at the poles, and a number of other issues. And in that context, Q can be seen to be true in some sense. For the purposes of formal logic, we have to assume that Q is completely true. It has the value true, and it doesn't have the value false. It can have only one of the two. It can't be a bit of both. Okay, so now we have those two symbols, and we want three more, which will be the hook, the wedge up, and the wedge down. And we'll have hook P, hook Q, P, wedge up Q, P, wedge down Q. Those are just formal expressions. What they mean, we have to start working out. So I'm going to give this explanation in terms of the meanings of these four expressions, but more usually in formal logic, we first go on to the truth tables, and then we use the truth tables to infer what hook P, hook Q, and so on mean. Okay, so if we say hook P is the Earth, the Sun does not spin, the Earth does not spin on its axis, and hook Q, the Earth, is not round. Hook, the P wedge up Q is the Earth spins on its axis and the Earth is round, and P wedge down Q, the Earth spins on its axis or the Earth is round. So what we mean is that hook means not, wedge up means and wedge down means or. But what do these mean in terms of formal logic? The effect is that they may change the truth values. So, for example, P is true, then hook P is false. So this is summarized by means of truth tables. In a truth table, we specify the truth of all valid combinations. So for hook, which is the not, we have two lines because P can be either true or false. And when the value of P is true, then the value of hook P is false, and when the value of P is false, then the value of hook P is true. If we look at the wedge up operator, which is and, then for every value of P which is true, Q can be either true or false. And for every value of P which is false, Q can be either true or false. So there are four possible combinations. And the and is true only if P and Q are both true, otherwise it is false. And that is the meaning of these operators. It's not that we have translated and into this, it is that we have defined the exact meaning of the wedge up operator. In terms of classic study of logic, we can prove that this truth table embodies exactly what classical logic understands by the and operator, but in fact this truth table is not dependent on classical logic, it just is a definition of how the wedge up operator works, and that is how it operates on true and false values of P and Q. And similarly for the or operator wedge down, and I'm sorry, there's another typing error there. We have that it is, again, we have these same four possibilities for P and Q, but now P or Q is true for is false if they're both false, and otherwise it's true. So they're called operators, and in Julia, not operator is the exclamation mark, the and operator are two ampersands together, and the or operator are two vertical lines. Now, why does formal logic need a formal language? Well, every expression must consist of symbols, and so we must be able to form expressions. And in particular, we must be able to form expressions that are equivalent to P and Q. We could try and list all the expressions that we want to have and give a symbol for each of them, but that will, of course, be incredibly long-winded. We'll need millions of expressions and choose one of them. That's basically impossible. So we have ways of combining, in Julia, formal expressions that are either true or false, and that means that Julia is actually a formal language. We have characters, and they give us values and names. And then we use delimiters and operators to form these names and values into expressions. So the rules of the formal logic that governs Julia then determines whether the expression is valid or not. So the result is that you can write an unbelievably large number of Julia programs. But in order for them to consist of valid expressions, you have to follow the rules of Julia's formal language and formal logic. And that is why formal language makes computers possible. They are generative. You can make new expressions from old ones. So it might be possible for a useful language to have only a few expressions, but Julia and all the other major computer languages allow a great many valid expressions, and they don't put any limit on how many such expressions are used to write a program. This is actually similar to writing a poem. You put one word after another, one line after another, and there's no set limit on how long your poem should be. The other point about a formal language is that because the rules are completely fixed and explicit, they can be mechanized. They can be made to be part of a machine. So in such a machine, you can represent the value true and false, and you can have an operator which turns true into false and false into true, so that is a not operator. At the level of the microchip, that is what happens. They contain many millions of tiny electrical circuits which are electronic versions of not, and or. And they transform values that are values equivalent of true and false. Basically, there are certain voltages. So formal logic is what makes a computer possible, and all modern computers are applications of formal logic. So let us go on and explain just how these formal languages really work, because that will give you an idea of what we're doing with Julia. I'm only going to give you a formal language which goes roughly as far as we have gone with Julia in lesson 1 and 2. So here we have characters, A, C, E, I, F, H, L, N, S, T, and the space character. That is what we've done in lesson 1. We used the characters from the International Keyboard to make strings, to make variable names, and to write the println operator function, and to write the include function. That was everything we did in lesson 1. And so the rules in this language then are that some letters are also vowels. They are E and A, E and I. Some letters are also consonants. They are C, F, H, L, N, S, and T. And so you see that this doesn't include the space character. Every expression must start with a consonant. The third rule. The fourth rule is that an expression may not contain two vowels next to each other. The fifth rule is that you can lengthen any expression by adding a character to it, and by that I mean adding it on the right, except that you can't have an expression with more than 100 characters, and you can't have an expression that ends with a space character. So that is so basically rules 1 and 2 specialize some of the letters. Rule 3 is about the start. Rule 4 is it excludes adding vowels next to vowels, and Rule 5 Rule 5 is about lengthening expressions and what happens at the end of an expression. Ad hoc can produce sentences like "that is it" and "that is it, I think." So curiously enough, it can't allow "I think that is it" because it violates Rule 3. It starts with a vowel, not a consonant. And some amusing expressions are possible. The think that I think that I think that I that think thinks, and the famous paradox, this sentence is false. These are all valid expressions in ad hoc 1. Similarly, what you've already learned in Julia is that very, very many valid expressions you can make just by making strings and assignments and variable names. If we read this last sentence as English, then we are not reading it as ad hoc 1. There is no way in which ad hoc 1 is actually an attempt to express English. If we wanted to make ad hoc 1 a language that expressed English, we would have to make lots and lots of additional rules, essentially translating between English and ad hoc 1. Similarly, in Julia, when we see Julia programs, there's a temptation to read them as English, such as "this sentence is false." In ad hoc 1, we read that as English. And actually, we should be careful not to try and do that too much. So Julia was written so that some of your intuitions from English translates easily into Julia. But it's by no means the intention to make Julia equivalent to all of English. And you cannot be sure that because something makes sense in English, it actually makes sense in Julia. You have to follow Julia's formal rules and formal logic. So in ad hoc 1, there's no empty expression. You can't write more than one line because there's no new line character and there are no delimiters. You can't do punctuation. In fact, all you can do is distinguish between valid and invalid expressions. You can't make ad hoc 1 into a computer language. It doesn't even have true or false in it. And it doesn't have logical operators, so we can't do the things that you need to be able to do in a computer language. It can't make a computer do something because it doesn't have anything that changes the computer memory. It doesn't have anything that makes a computer print things on the screen. So it's very, very far from being a computer language, but it is a formal language, and it does distinguish between valid expressions and invalid expressions. And that was the main point I wanted to make. So finally, let's go on to programming, poetry, and truth. Beauty is truth, truth, beauty. That is all you know on earth and all you need to know. Famous lines from a romantic poet in the 19th century. So Julia allows you to make very, very many expressions. You can choose your own names for variables. You can write your own functions. You can choose when to employ them. You can structure the logical operators in your program. And you are expressing yourself when you do that. It is exactly the same sort of thing as a poet does, but you're expressing yourself in a computer language, not in poetry. And because you're doing it in a computer language, you are causing things to happen. Numbers are calculated, pictures are drawn, documents are printed, and many more things. The poet aims at different effects, wants to get reactions from the readers and listeners, supply memorable descriptions, catch a mood, but a programmer is also using their skill to achieve definite purposes. So there's a similarity. And truth is a very big part of it. Truth is central to logic, as we saw above, and computer programs depend utterly on the computer programmer keeping a very strict eye on whether their logic maintains truth. So paraphrasing Keats, we might say, code is truth, truth code. That is all you need at the keyboard. I want to make the point that there is a truth embodied in fine poetry, and it is not the same as the truth in beautiful pottery. And that is not the same as the truth in a computer program. But all three, pottery, poetry, programming, they are using the expressive power of their medium to get at the truth that their medium can embody. And in that sense, programmers are like artists and poets. Okay, so let's summarize. Logic is the study of correct forms of reasoning. Formal logic use formulae to do logic. Truth tables spell out exactly how logical operators work. And to be useful, a formal logic must be part of a formal language. And a formal language is a set of symbols and a set of rules for combining them. And all of this means that Julia itself is a formal language. It's just that it's a formal language for interacting with a computer. A programming language is capable of endless variety of expression, and writing code is as creative as writing poetry or music.